So welcome. So we'll discuss the previous question paper. So first question is examine the function f of x equal to x squared cos 1 by x if x is not equal to 0, 0 otherwise. That means at x equal to 0. This function is of bounded variation in the closed interval 0, 1. So let us see the definition. There are many definitions and properties related to this concept. Let us see one definition, that is, let f be a function defined on the closed interval ab. And on ab, let us take a partition, that is p, that is x0, x1, so on, xn. And also delta fk, that is, which is defined as f of xk minus f of xk minus 1. That is the difference between the value of the function at x equal to k and the previous point, that is at x equal to k minus 1 for various values of k, that is from 1 to n. So then if there exists a positive integer m such that summation over k from 1 to n mod of delta of k less than or equal to m. This is for all partitions defined on the closed interval a comma b. So then the function defined is said to be of bounded variation on ab. This is the basic definition related to bounded variation. Now if we take the example, so here to prove the function f of x is of bounded variation, we will take its derivative and prove. Okay. So now we'll find its first derivative f dash of x. Here uv formula we applied. So x squared derivative is 2x and cos 1 by x plus x squared into derivative of cos, that is minus sine, into derivative of 1 by x, that is minus 1 by x squared. Okay. If we simplify, f dash of x is 2x cos 1 by x plus sine 1 by x when x is not equal to 0, 0 when x equal to 0. Now if we take mod of f dash of x, so which is less than or equal to 2 plus 1. Right? So that is, if you remember this, mod of a plus b less than or equal to mod a plus mod b, right? So if we remember this, so by using this we can write this as mod of 2x cos 1 by x plus mod of sine 1 by x, that is nothing but 2 plus 1, that is mod of f dash of x less than or equal to 3 for every x in the closed interval 0, 1. So that is as discussed. Now it is mod of f dash of x less than or equal to m. Therefore, we can say f of x is of bounded variation in the interval 0, 1. So this is one example. So next, state chain rules for Jacobians. So to understand this question, first we need to understand what is Jacobian and how this chain rule, which is familiar in terms of our regular differentiation, in terms of Jacobians. So now let us define Jacobian. Let x is a function which depends on u and v, that is u and v are independent variables, x is an independent variable. Similarly, y, which depends on u and v, right? Now from this we understand, if we want to find derivatives, we can find, right, we can find derivative of x in terms of u, derivative of x in terms of v, because x depends on u and v. X is independent variable, x is dependent variable and u and v are independent variables. Similarly, we can have partial derivative of y with respect to u, partial derivative of y with respect to v, right? We can find that. So with this understanding, let us define the Jacobian. So when let x is function of u and v, y is function of u and v, then Jacobian of xy with respect to uv. So that is Jacobian of xy with respect to uv, or we can write like this, which is nothing but the determinant consisting of all partial derivatives, that is dou x by dou u, that is x derivative with respect to u with respect to v, y is derivative with respect to u, y is derivative with respect to v. So this is called as Jacobian of xy with respect to uv. Now let us see chain rule in terms of the differentiation what we are already familiar with. Suppose x is a function of u and v, where u and v are functions of some other variables s and t. So x is function of u and v, where u is function of st as well as v is function of st. X is function of u and v, where u and v are functions of s and t. So here when s varies, u varies, yes, it's also varying, x also varies, so that it is a partial derivative. Yes. Right. So that is how we find that chain rule is dou x by dou s. X is function of u, so what's dou x by dou u, where u involves s, right? Therefore dou u by dou s. Right? So this term is, so change in x corresponding change in u corresponding change in x, right? Change in s corresponding change in u, when u changes x also changes. This part takes care of the change in x when s in turn u varies. Similarly, x is a function of v is also a function of s. When s varies, v also varies. When v varies, x also varies. So this term indicates the change in x when s varies, in turn v varies. Yeah. So this total is dou x by dou s, that is total derivative of x with respect to s. This is the chain rule concept what we are familiar with. Now we'll extend this understanding in terms of Jacobians. Very simple, right? So let x and y are functions of uv, where u and v are functions of p and q. Now immediately we'll same thing, like we want Jacobian of xy in terms of p and q, that is Jacobian of xy in terms of pq is nothing but Jacobian of x first with respect to u v, next Jacobian of uv with respect to pq. Simple, right? Jacobian of xy with respect to uv, Jacobian of uv with respect to pq. Actually this can be simplified and proved, but here the question asked is only the discussion related to chain rule of Jacobians. Right? Okay. Next, state the properties of line integrals. Very simple question. So the line integral, that is integral over a curve or the line. Generally it's a curve. Integral defined over a curve is called as a line integral. The first property is integral over c lambda into f of xy plus mu into g of xy dx, where lambda and mu are constants or scalars. Right? This is like what we do, right, in case of our regular integration. In the same sense, this is equal to lambda into integral over c f of xy dx plus mu into integral over c g of xy dx. This is the first property. Second property, if the line integral, that is f of x comma y dx, is over the union of two curves c1 union c2, right? It is something like that. Suppose this is c1, this is c2, right? Maybe if you take the closer one also, not a problem, right? If you want to find the integral, line integral over c1 and c2 union, that is the total curve if you take as c, that is c1 union c2, it is understood, it is nothing but integral, line integral along c1 plus integral, line integral along c2, right? That is what it indicates. So line integral over C1 union C2, that is a complete curve C, equal to integral over first curve C1, integral over second curve C2, right? So that is second property. Third property is, if two functions f of x are such that f of x less than or equal to gx for every x belongs to C, then the corresponding line integrals, that is integral over C f of x dx, is always less than or equal to integral over C g of x dx. Okay? These are the few properties related to line integrals. So next is the definition of MP inverse, Murray-Penrose inverse of a matrix. Right? This is a basic definition of. Let this, if you remember, generally we talk about the inverse of a matrix when it is a square matrix, right? Whenever a square matrix, then we are familiar with respect to inverse of a matrix. So here MP inverse comes into picture or comes for the discussion when it is not a square matrix, right? So if it is not a square matrix, then we find its MP inverse. So what is the definition? The same understanding whatever we had in terms of a regular inverse, mostly the same comes here also. Right? Let A be a matrix of order m by n, that is, which is not a square matrix, it is a rectangular matrix. Then suppose there exists some matrix denoted by A plus, right, which satisfies the properties. First one is A into A plus is symmetric, and also A plus into A is also symmetric. Okay. And third one is A into A plus into A equal to A. So very simple, actually what we are saying is inverse, right? So A plus, if this is inverse, right? Inverse into a matrix is I into A is A, right? So other properties, A plus A plus is what? So we know this is inverse into matrix is I into A plus is A plus, right? So if A plus satisfies these four properties, then it is called as MP inverse of a matrix. Okay? So one is symmetry related to the both combinations. Other one is, it is almost like identity property, right? With the combinations A plus A plus A equal to A plus A plus equal to A plus. Right? This is the definition of MP inverse of a matrix. Next, Hermite form of a matrix, right? And write an example. So what is Hermite form? Right? Let us have a matrix of order n by n, right? So if it satisfies the following properties or conditions, then it is called as Hermite form. So what are those conditions? First is the H is an upper triangular matrix. Right? So H is the first and very important thing is upper triangular matrix. Second one, only zeros and ones are on the diagonal. We know, right, in upper triangular matrix, all the elements below this are zeros, and here we'll have elements. In this diagonal, we need to have only ones and zeros only. That is the second condition. Third condition, if a row has a zero on the diagonal, if anywhere in the diagonal, if row is having a zero, then every element in that row is zero. Then the rest of elements in that row has to be zeros. Right? Whenever there is a zero in the diagonal, then the rest of the elements in that row are zeros. Right? Next property is, if a row has 1 on the diagonal, right, 1 on the diagonal, then every other element, right, every off diagonal element in that row column, in that row is 0. Right? If there is a 1, right, if there is a 1, then every off diagonal element are zeros, right? This is okay. So similarly here, right? Actually here it is a column. It is not true, right? If a column is having a 1 on the diagonal, in that column rest of the elements are zeros, right? This is a column actually. Yeah. So next question is find the matrices of the quadratic form, right? 2x1 square 8x1 x2 6x2 square. This is the quadratic form. So a expression which is homogeneous of degree 2, expression which is homogeneous of degree 2 is called as a quadratic form. Here if you see, this is order is 2, this is order is 2, this is order is 2 and homogeneous, therefore this is called as a quadratic form. Now we need to write its matrix form. So how we write is, so it is general form is x transpose x, where A is its matrix, right? X is also a matrix. X consisting of the variables that are there in the quadratic form given. It contains two variables, right? x1, x2. So column vector or column matrix consisting of the variables that are there in the quadratic x1, x2. So it's a transpose here. Then the matrix is very simple. So for our understanding sake, we can write this as x1, x2, x1, x2. Now this is x1 square term. So 2x1 square. This is x2, x2. Therefore it is x2 square term. That is 6x2 square. So next this is x1, x2. This is x2, x1. So this 8x1, x2 can be written as 4x1, x2 plus 4x2, x1, right? Okay. So 4 comes here, 4 comes here. So we have to make it half and distribute in the respective positions, right? So this is the matrix form of a quadratic form, which is in general x transpose Ax. Some people write it as x transpose Ax like this, right? Where A is a symmetric matrix. Okay. Next, another important definition is define index and signature of a quadratic form. Right? So here what is how to define index and signature. So consider the quadratic form of x transpose Ax with rank R. So rank R means, if you remember the discussions related, so we have sum of squares x transpose Ax can be written as sum of squares form. That means it will have only square terms. And rank R means the total number of terms are R. That means it's the canonical form of x transpose X is y1 square, y2 square, y and so on, yr square. Okay. So this is the canonical form of x transpose X. Right? So here in this we have a combination of positive terms as well as negative. Total terms are R, that is nothing but the rank of the quadratic form. And here if you see up to this all are positive terms, right? That is S terms are there which are all positive terms, right? So that is called as index, right? So then that is the definition. The number of positive square terms, that is S here, in the canonical form or sum of squares form of x transpose X is called as index, right? This is one definition. Next, other one is, so in the canonical form or sum of squares form, let some terminologies. Let R denotes total number of terms, which is called as rank. Yes, the number of positive terms, that is just now we discussed, which is index. So R minus S is nothing but number of negative terms. Then signature is nothing but the number of positive terms minus R minus S, that is 2S minus R, that is excessive positive terms. Nothing but signature, right? 2S minus R is called as signature. Where what is S? S is number of positive terms, R is total number of terms, that is rank of the quadratic form. Right? These two are important definitions, rank and index. Next, investigate the nature of critical points of the function f of x by x power 4 plus y power 4 minus x square minus y square plus 1. So nature means here we have to discuss the maxima or minima, right? That is, and at critical points means the points at which its first derivatives become 0. Dou f by dou x equal to 0, dou f by dou y equal to 0. Right? So at the points at which the first derivatives becomes 0 are called as critical points. And we want to find out here, we have to find out what are the critical points and what happens at these points, whether it becomes maxima or minima, neither maxima or minima, like discussion we have to have here. Right? So based on this understanding, first what we have to do, first we have to find critical points with the help of the first derivatives equal to zeros. Okay. So now we'll take. So the function f of x y is x power 4 plus y power 4 minus x square minus y square plus 1. So now its first partial derivative with respect to x equal to 0. 4x cube minus 2x equal to 0. So second is partial derivative of f with respect to y equal to 0, that gives 4y cube minus 2y equal to 0. Right? As discussed, so first derivative is equal to 0, so we get this. Now we have to solve these two equations. That means we have to find out the points at which the first derivatives become zeros. Right? Now if we take the first one, how to solve depends on the problem. Here very simple. First, from the first one, if we take x common, x into 4x square minus 2 equal to 0. From this x equal to 0, 4x square equal to 2x equal to plus or minus 1 by root 2. Similarly, the second equation, taking y common, then we get y equal to 0, y equal to plus or minus 1 by root 2. So here total we have 4 points, because here plus or minus 1 by root 2, here also plus or minus 1 by root 2. Here we'll have 4 points at which the first derivatives are becoming zeros. That means 4 critical points. Right? So now we'll see what are the conditions to say whether it is maxima or minima. Right? So various approaches are there. It's the easiest approach. Right? So we'll find the Hessian matrix, H matrix, consisting of its second derivatives, because the maxima or minima depends on the second derivatives. Just for our understanding, in case of single variables, dou square y by dou x square greater than 0 at a point, then we say minimum. Less than 0, we say maximum. Right? At any point, at the point, if the second derivative greater than 0, we say it becomes minimum. If second derivative less than 0, we say at that point it becomes maximum. That means the nature of the function depends on second derivatives. So here one approach is, let us have this matrix. So dou square f by dou x square, dou square f by dou y dou x. That is the second derivative of f, right? That is dou square f by dou x square and dou square f by dou y dou x. Similarly, dou square y by dou y dou x. Here actually dou x dou y, you can write this as dou x by dou y, is more for more clarity's sake. Right? Right? Similarly, dou square y by dou y by dou x. These two are same, we know, and second derivative of f with respect to y. Right? We will find this one. Then actually one approach is, so this is the we'll take the principal determinants. So based on the principal determinants, we can comment whether it becomes maxima or minima. So principal determinants means this is the first principal determinant and this is the second principal determinant, right? As shown here. Right? If both determinants, principal determinants, are greater than 0, that is h greater than 0, that is here h in the sense delta of h. that is sorry determinant of h greater than 0, and this principal determinant dou square f by dou x square is also 0, then it is minima at that point. Second one, that of this matrix greater than 0, but the first principal diagonal principal determinant is less than 0, then it is maximum, right? If the data of h itself less than 0, then we say saddle point, right? So neither maximum nor minimum. If det equal to 0, we cannot say, it is undecided. We can't say anything related to its nature at that point. We need further investigation. Right? So it means when we want to find the nature of critical points, we'll find this matrix with second derivatives. Then we'll find its determinant. Right? So whether greater than 0, yes, there is a possibility that it becomes minimum or maximum. Then we'll see its first principal determinant, that is dou square by f by dou x square. Depending on greater than 0, it becomes minimum. If it is less than 0, it becomes maximum. Otherwise, these conditions. Right? So now this we have to do for all the 4 points to say what is the nature of the function at these points. Right? So as seen, we have 4 points. Actually not plus or minus, plus 1 by 2, right? 0, 0, 0 plus or minus 1 by 2, plus or minus 1 by root 2, 0. That means here actually if you see, almost is 0, 0, many number of points, right? Because with plus 1 by root 2, 0, 1 point, minus 1 by root 2, another point, like this. So many points are there which are saddle points. Is not, the term is wrongly mentioned here, they are stationary points. Right? They are not saddle points, they are stationary points. Right? Saddle point is something where which becomes neither maximum nor minimum, right? Yeah. Okay. So now at each point, first let us take h, dou square f by dou x square, its second derivative 12x square minus 2. Here in this case, first derivative with respect to y is not having any x term, similarly y term. So this with respect to x function, derivative of f with respect to x as well as y becomes 0, and this is now very simple. If at 0 comma 0, what happens, this h determinant of h becomes 4, which is greater than 0, and at the same point what happens, this 12x square minus 2, 12x square, when x equal to 0, it becomes minus 2, right? That means the first principal determinant or minor, whatever the term is minus 2, which is less than 0, and the data of the matrix is greater than 0, therefore maximum at the point. First is this is greater than 0, so that means it becomes either maximum or minimum. Next we have to check this to conclude whether it becomes maximum or minimum. Here this dou square f by dou x square is less than 0, therefore it becomes maximum at 0 comma 0. Right? Next, similarly at 0 plus or minus 1 by root 2. Here squares are there, that's why we are taking this as a point. Otherwise, we have to do this with 0 plus 1 by root 2. Other one is 0 minus 1 by root 2. Because here this square is there, no x term, that's why it doesn't make any difference. Right? So we'll find, similar to this, we'll find data of the matrix H. With this, if we substitute x equal to plus 1 by root 2 or minus 1 by root 2, this becomes minus 2. Similarly, put y equal to 0. Sorry, it is x equal to 0, and y equal to this point. If you substitute, we'll get this, which is minus 8. So this determinant of the matrix, Hessian matrix, is 0, less than 0, therefore it is saddle point. If you remember, only when it is greater than 0, then we look for the other case to whether it becomes maximum or minimum. It is less than 0, therefore saddle point. Similarly, at other point, plus or minus 1 by root 2 comma 0. So here the data of the Hessian matrix is minus 8, which is less than 0, therefore saddle point. Right? So next, other point plus or minus 1 by root 2 plus or minus 1 by root 2, then that equal to 16, which is greater than 0, right? So immediately we see this, right? 12x square minus 2, 12x square minus 2, what happens here? 12 into x square means 1 by 2 minus 2, right? So this becomes greater than 0, right? So greater than 0, that means it becomes minimum at this point. So like this we have to find the nature of the function at the points, right? So this can be asked in many ways. Same question can be asked like find maxima, minima of the functions, discuss the nature of the function, right? Like this. Okay. So next is define Jacobian function of n variables, right? N variables. So very simple. It is like what already we discussed in Jacobian. So one is we have to define it for many variables. Let u1 is a function of many variables x1, x2, so on, xn. Right? Similarly, u2 is a function of many variables x1, x2, so on, xn. Similarly, and so on, un, which is function of x1, x2, so on. That means now immediately we understand. So we can have derivatives of u1 with respect to x1, x2, so on, xn. Derivatives of u2 with respect to x1, x2, so on, xn. Similarly, u3, similarly, so on, un. Now, the Jacobian of u1, u2, so on, un with respect to x1, x2, so on, xn. So, very simple Jacobian of u1, u2, so on, un in terms of x1, x2, so on, xn. So, which is nothing but determinant. Very simple as discussed. Derivatives of u1 with respect to all the variables on which it depends. U derivative with respect to x1, u1 derivative with respect to so on, xn. Similarly, u2, its derivatives with x1 with x2 with xn, so on. Un with x1, un with x2, un so on, xn. So this is how the definition of Jacobian what we discussed can be extended in terms of n number of variables. Okay. So next question is, so define power series, define Taylor series, define Lorentz series, and zeros and folds. Even when we discuss complex analysis, we have to see various kinds of poles, right? Okay. So what is a power series? A series of the form a0 plus a1 into z minus a plus a2 into z minus a whole square and so on up to infinity, or simply it can be written as summation over n from 0 to infinity an z minus a whole power n. This is called as power series in terms of z minus a. Right? Very simple definition. Next, Taylor series. Right? Let f of z be a single valued function which is analytic inside and also on a circle C except the point z equal to a. That is, f of z is analytic everywhere except at the point z equal to a. That means then this function can be written as f of a plus h equal to f of a into h into f dash of a, h square by 2 factorial f double dash of a plus so on, h power n by n factorial fn, nth derivative of f at a plus so on. Or if we take a plus h equal to z, right? So then it becomes f of z equal to f of a plus z minus a into f dash of a, z minus a whole square by 2 factorial f double dash of a and so on, nth derivative of f at a by n factorial into z minus a whole power n. Right? So either we can have this form or this form. Right? That is the Taylor series in terms of h or Taylor series in terms of z minus a. Okay. Next is Lorentz series. So let C1 and C2 be concentric circles of radius R1 and R2 at center A. The two concentric circles we know, right? Two circles which are concentric, right? So where radius center is A with radius R1, radius R2, right? Okay. Then suppose that f of some function f of z which is single valued and analytic on C1 as well as on C2 in the angular domain R between C1, that means this R, this is R is this, right? Right? Then f of z equal to summation over n from minus infinity to plus infinity an into z minus a whole power n, where an is 1 by 2 pi I circulation over C f of z by z minus a whole power n plus 1 dz, where n equal to 0 plus or minus 1 plus or minus 2 and so on, right? Where C1 and C2 are traversed in the positive direction. Actually, some people they write this as two parts. One is the expansion of this from minus infinity to 0, and the other part is 0 to infinity, because it consisting of positive powers as well as negative powers. When n equal to minus 1, minus 2, minus 3 and so on, this becomes 1 by z minus a whole square whole cube and so on. That is one part. When it takes n equal to 1, n equal to 2, it becomes z minus a whole square and so on, right? This is some people write like this. So that is what is called as Lorentz series. Okay. Next, zeros. So let us take a function f of z and a point z naught. If f of z naught equal to 0, then z naught is called as a 0 of f of z, right? This is a regular definition, right? So this is simple zero, right? Suppose if we take f of z which is analytic and it is having 0 of order n at z equal to z naught, then what does it mean? Then what happens is the f of z naught becomes 0, f dash of z naught becomes 0, f of n minus 1 z naught becomes 0, but at n, that is f of n z naught is not equal to 0. So then it is called as 0 of order n. Right? Okay. Right. Next is a pole. If function f of z is having the form f of z equal to summation over n from minus infinity to plus infinity an z minus z naught whole power n. So this can be written as summation n equal to 0 an z minus z naught whole power n, that is for positive values. So for negative values, this, right? So in this, if the principal part contains a finite number of terms, right? So in this principle, this got only finite number of terms, then z equal to z naught is called as pole of order n, right? So in that case, what happens when z equal to z naught, this becomes 0, right? So then we say z equal to z naught is a pole of order n. Next is a solution to a non-homogeneous system Ax equal to b exists. We know this actually, right? So when we say a system of non-homogeneous equations Ax equal to b is consistent or solution exists when rank of A equal to rank of b, right? Where B is the augmented matrix, right? Where it contains A as well as B, right? This is already we are familiar, right? Again, I repeat. The system of the non-homogeneous system of equations Ax equal to b is said to be consistent. That means solution exists if and only if rank of A equal to rank of b, where B is augmented matrix, that is A and B. This is so that will prove now. Right? And this is a necessary and sufficient conditions. This is, if you see here, it is a necessary and condition. That means by taking that a solution exists for Ax equal to b, we have to prove rank of A equal to rank of b. By taking rank of A equal to rank of b, we have to prove that the system is having a solution. Right? We'll see how to prove. So necessary part is, so we have to assume that solution exists to Ax equal to b. From this we have to prove rank of A equal to rank of b. Repeat, this b is augmented matrix which is AB. Okay? This is our matrix. Okay. So Ax equal to B, we know is nothing but we can write this as A1, A2, so on, An. Okay. And x is x1, x2, so on, xn, that equal b1, b2, so on, bn. Right. So now this can be written as summation over I from 1 to n, ai xi equal to b. If you simplify this, a1 x1 plus a2 x2 plus a3 x3 equal to b1, similarly b2, similarly b3, like this. This is another form that we can write. Right. The system can be written as summation over I equal to 1 to n, ai xi equal to b. Right. That means the vector space spanned by a1, a2, so on, an of a is same as the vector spanned by the columns of b. Right? So that is what we understand from this. Columns of b actually here. Now that means what we say, dimensions of the vector space by the columns of A is same as the dimensions of the vector space spanned by the columns of B, right? So dimension is same. We know the definition of dimensions, that is nothing but number of linearly independent vectors of A is equal to number of linearly independent vectors of the matrix B. And we know this nothing but this number of linearly independent vectors is nothing but rank of A, right? So this is similar to that, therefore rank of A. That means rank of A equal to rank of B. That means condition is necessary. So sufficient part, we have to assume that rank of A equal to rank of B. Then we have to prove that there exists a solution for the system of equations given by Ax equal to B. Right? Now let us assume rank of A equal to rank of B equal to R. Then we have to prove that there is a solution to Ax equal to B. That is what we have to prove. Now if rank of A equal to R, then there are exactly R columns in A which are linearly independent. Right? That is what we understand from the definitions, right? That means they are A1, A2, so on, AR. Next, every other column of A must be a linear combination of these R columns, right? That is what we discussed when we discussed the rank of a matrix, right? And linearly independent, dependent kind of thing, right? That is, since rank of B equal to R, there are exactly R columns in B which are linearly independent. Here, because rank of B is also R, so then they are linearly independent. Therefore, A1, A2, so on, AR. So similar to the previous discussion, every other column of B can be obtained as a linear combination of these R columns, A1, A2, so on, AR. Right? That means now that is B is nothing but B can be written as A1 x1 plus A2 x2, so on, AR xr. If we let xi equal to 0 for I is from R plus 1, R plus 2, so on, n, suppose, then this B can be written as, the equation 1 can be written as A1 x1 plus A2 x2 plus AR xr plus AR plus 1 into 0 plus AR plus 2 into 0, so on, AN plus into 0. Right? Okay. That is, from this what we understand, because this, if we take the vector that is defined as x0, x1, x2, so on, xn, so I'm remaining all zeros transpose, right? This is transpose. Then this is nothing but B equal to A into x0, where x equal to this one. So that means Ax equal to B is the system where x0 is satisfying. Therefore, x0 is a solution of Ax equal to B. That means there exists, whenever rank of A equal to rank of B, there exists a solution to the system Ax equal to B. Right? So this is how to prove. So we need to practice this actually to get more comfort in proving this. Okay. So next one is, show that the range of values of two congruent quadratic forms are same. Right? We'll see it. So consider two congruent quadratic forms, right? That is, one is X transpose AX, Y transpose PY. So if you remember the discussion, so when we call two quadratic forms are congruent if their corresponding matrices A and B are congruent. Right? That is the definition. So here, so consider the X transpose X and Y transpose BY, which are congruent quadratic forms. Then immediately our understanding is the matrices are congruent. Two is congruent. Right? So if congruence definition if we see, then we say if a matrix is said to be congruent, there exists a non-singular matrix P such that B equal to B transpose A. These are the definitions. If B equal to P transpose AB, then we say B is congruent to A. B is congruent to A. B is congruent to A. This is the basic definition. Now we'll proceed further. Now let us consider a transformation X equal to Py. Then immediately we understand Y equal to P inverse X. So now if we take any value of x1, right, that means any value of x1, that is x1 transpose ax1 of the first quadratic form, right, then if you take y1 transpose by1, if we take, where we took y equal to p inverse x, right, so we can write this as p inverse x1 transpose into p inverse x1. We are replacing y1 by p inverse x. Now this can be written as x1 inverse p inverse transpose b p inverse x1, and we need to remember this p is nothing but p transpose ab because they are congruents. Right? Now we continue the substitution. Right? So x1 transpose p inverse transpose b p inverse x1. This is what we had. Now we replace this b by its p transpose AP because they are congruent to each other. B is congruent to A particularly. Right? Now this can be written as x1 transpose p inverse transpose p1 AP. Now this we can combine this, right? This we can take as, and we know AB whole transpose equal to B transpose A transpose, right? If we use this, we can write this as P into P inverse whole transpose, right, into A. Similarly, P into P inverse whole transpose. I think no transpose here, into x1. Right? So we know P into P inverse is I. Here also it becomes I. Then what happens? It becomes x1 transpose A x1. If you remember earlier what we have taken y1 transpose b y1, and we used the transformation y equal to p inverse x1, and also we used the congruency property, that is b is replaced by p transpose ab. So from that we are getting y1 transpose b y1 equal to x1 transpose ax1, right? So that means what from this, because these two are the same, that means we say the corresponding quadratic forms, that is y transpose by, x transpose ax, are the same in terms of their ranges, because these two quadratic forms are similar for some value of x1 there and some value of y1 here, right? Okay. So this actually this we need to remember it as, so this one and this y equal to p inverse x, and replacing b by p transpose a p, and proving this y1 transpose b y1 equal to x1 transpose b x1. If we are able to prove it, then we say these two are having same ranges. Okay. Next one is consider this quadratic form x1 square plus 2x2 square plus 3x3 square plus 2x2x3 minus 2x3x1 plus 2x1x2, and hence find its rank as well as index. Right? So already we have seen in the earlier discussion that first we need to convert this into canonical form or sum of squares form, right, from which we can find rank as well as index. So the total number of terms in this form is called as rank, the positive terms are called as index, similarly signature, etc., 2s minus r. So here important thing is, so we have to convert this quadratic form into canonical form, or sum of squares form. Right? So how to do it? Right? So first we need to write this in matrix form. Right? So this also we discussed earlier in one of the questions, writing the quadratic form in terms of matrix form. So that is x transpose ax, x transpose ax. So first x is the column vector or column matrix consisting of the variables. This quadratic form involves three variables, x1, x2, x3. Now important step is writing matrix. So as I told, right, we write this as x1, x2, x3, x1, x2, x3. So first you see here x1 square, so 1, 2x2 square, so 2x2 square, 3x3 square, so 3, so over. Next x2, x3, we have to distribute it equally. As if you remember, x2, x3 means this one, right? This is similarly x3, x2. Right? Next to minus x3, x1, right? x3, x1 is this, the x1, x3. Similarly x3, x1 minus 1. 2x1, x2, half here, 1x1, x2, 1x2, x1. Right? Like this we have to distribute. Right? So this is the matrix. Now why the matrix A is important for us? This we have to use to convert this quadratic form into canonical form, so that we can find its nature. Okay. So first what we have to do is, we have to, because the canonical form contains only square terms, that means only diagonal elements, rest of the elements are zeros. Right? So for which we need a transformation, right? We'll see it. So for that what we have to do is, let us take A equal to IAI. I think I is an identity matrix, it doesn't make any problem or any difference. Right? So take the matrix A as it is, I as it is, A. Now the aim in doing what we have to do is, we have to convert this into a matrix consisting of only diagonal elements. Right? Only diagonal elements by using row operations as well as column up. But finally we need to have this as something like P transpose AP kind of thing, right? So finally we need to have matrix and its transpose here, and here we need a matrix with only diagonal element, right? So for which what we have to do is, so apply here we can first we have to, because we need transpose here, right? Rows, I think there should be some relation between. So what we do is to convert this into a matrix consisting of only diagonal elements. So first apply row operation. Here if you see, first we applied row operation, R2 is R2 minus R1, right? So first we are applying R2 minus R1, right? So when we apply the row operation, apply on this first matrix and the first matrix that is there in the right hand side, right? So next, very importantly, we have to apply similar column operation on the matrix in the left hand side compulsorily. In the right hand side we have to apply the column matrix in the last identity matrix or last matrix, right? So here row operations as well as column operations we apply, but the thing is, importantly, whenever we apply a row operation we have to apply on this identity matrix. This is the first one. Then next step we have to apply similar column operation on the left hand side and also on this matrix, right? Okay, that is very important. So one operation is completed means we have to apply row operation and similar column operation, right? Then only we'll get the P transpose A equal to B, therefore the matrix B is congruent to A. Okay, so clear? Now we'll see it quickly. So applying as discussed, right, R2 minus R1 and C2 is C2 minus C1, then we get this matrix. Okay. So first this is after applying row operation. If you see a row operation on this on this we have to apply both row operation on this we get. Next, without, we won't do anything on this, we apply similar column operation on this and column operation on this. Right? So practice this. So next we'll try to make this as zeros. Right? So we want only diagonal elements are needed. So what we have to do, R3 is R3 plus R1 is, so we have to apply R3 is R3 plus R1 on this matrix and on this matrix. After that we have to apply C3 is C3 plus, similar column operation. Right? So here, so this is R3 is R3 plus R1 applying on this and this. Right? Next similar column operation on this matrix, then we get this, then no change here as it is. So applying C3 equal to C3 plus C2, we'll get this. So now we'll see whether we are able to get the form required. No, still it is not there, right? So we have to make this as 0, this as 0. Then suitable operation we have to do. R3 is R3 minus 2R1, R3 minus 2R1. Similarly, C3 minus 2C1, like this. So this is, just practice it, otherwise it takes more time. So row operation will get this, similar column operation will get this, row after applying row operation will get this, no change in this. So next column operation we have to apply on this, we'll get this one. Here no change as it is, copy paste, and here we have to, after applying similar column operation, we'll get this. Now if you see here, we got 1 1 minus 2, right? So this is B. If you see here the matrix P and its transpose we are getting, that is B equal to P transpose AP. That means we got B is congruent to the matrix A. Once we got this, then the matrix P, etc., then we can have canonical form or sum of squares form in terms of some other variables we write. So let us take Y matrix consisting of Y1, Y2, Y3, and the diagonal matrix what we got now, right? Congruence matrix 1 0 0 0 1 0 0 0 minus 2 and transpose of Y. Simply it gives, because only diagonal elements are there, right? Y1 square, Y2 square minus 2Y3 square, right? So this is called as canonical form or sum of squares form. This is very important. Directly they can ask us to write the canonical form of given quadratic form, or they can ask us to discuss the nature of the quadratic form. That means nature in the sense we have to find rank, index, then based on that we'll comment whether it is positive, definite, semi-definite, etc., etc. But basic concept is this: converting the given quadratic form into sum of squares form or canonical form. Right? So once we have this, very simple, the A is non-singular, that are not equal to 0, or the number of terms that are there in the form, canonical form is 3, therefore rank is 3. Then S index is number of positive terms. Here this is positive term, this is positive term, so therefore this is. Here in this question they asked for rank and index only. If signature, then we discussed, it is 2 into S minus R, 2 into the index is 2, 2 into 2 4 minus 3 1, right? So this is important, right? So nature means we have to find rank, index, signature. Based on that we have to comment on its whether it is positive definite, positive semi-definite, positive negative definite, negative semi-definite, indefinite. All those things we can conclude based on this rank, index, signature. Okay. Next, if A equal to Aij, the matrix, is positive definite when det of A is less than or equal to A11, A22, so on, An. That means det of A less than or equal to the product of diagonal elements in the matrix, right? Which is, it can be written as this, some product we can write like this. Okay. Then the matrix is said to be positive definite. So how to prove it? Here we'll prove it for n equal to 2, n equal to 3, and generalize it. Right? Let us take n equal to 2. That means consider a matrix A, A11, A12, 21, A22. Now if we go for its determinant, which is nothing but A11, A22 minus A21. Right? Right? So here this is nothing but a11 a22 minus this a12 into a21 always greater than 0. And from the, because here what the reason is, the reason for this is all principal minors are consistently positive. All principal minors, that is a11 a22 are all consistently positive, and this a12 whole square, a12 a21 are is nothing but a12 whole square, which is always greater than or equal to 0, right? So therefore what we can say is that det of a is less than or equal to a11 into a22. From this we can say, so det of a less than or equal to a11 into a22. Similarly, if we take n equal to 3, so matrix A here, and if we take det of a, right? So det of a if we take, so you can take det of a, I think we know how to find the det of a. Here for this we'll use simple approach, that is a33 into, it's a minor cofactor if you remember, a11 12 a21 22 minus a13 a23 into adjoint of a12 12 a21 a22 into a13 a23, right? So we are not going to write it for all, right? So here we are expanding the determinant along this, right? So first a33 into its minor or cofactor, minus similarly a13 into say a23 into, that can be written like this, you can verify it. And here we know adjoint of a11 a12 a21 a22 is always positive definite, because this a11 a12 a21 a22 is positive definite, as we proved when n equal to 2, that we are making use of it. So this is positive definite, therefore adjoint of that is positive definite, that is what we are using here. So then det of a less than or equal to a33 into a11 a12 21 a22, right? Which is less than or equal to a11 a22 and a33, right? So that is det of a less than or equal to, now the same can be extended further, right? So a11 a22 a33 so on an. So if you see here, we tried with n equal to 2 and we used it here. So this matrix is positive definite. So then we are getting it for n equal to 3, where det of a less than or equal to a11 a22 a33, and we can generalize it for next. When we go further, we will make use of this. When n equal to 3, it is positive definite, right? So then we can try for n equal to 4 and so on. So continuing the same way, we will get this. So next is state and prove Cauchy squares and Hadamard inequalities. This is another important thing. So here we will discuss Cauchy squares inequality. Right? For any two n by n real column vectors x and y, we have x transpose y whole square less than or equal to x transpose x y transpose y. So this can be written as, if you take y as y1 y2 so on yi, if you take x as x1 x2 so on xi, then this can be written as becomes xi yi, summation I is from 1 to n xi y whole square. It is like, if I take y equal to y1 y2 so on yi, if we take x equal to x1 x2 so on xi, then if you take transpose of this x transpose, and if you go for multiplication of y, then what we get x1 y1 x2 y2 x3 y3 like this, right? That is what is meant by this. Summation I over I from 1 to n xi yi whole square less than or equal to. Now it is x transpose x, nothing but x1 square x2 square so on x, that is similarly yi square, right? Now here, that means we need to show this one, right? X transpose y whole square less than or equal to x transpose x y transpose y, right? So that is, instead of, that means nothing but if you just rewrite this one, x transpose x into y transpose y minus x dash y whole square greater than or equal to 0, right? Simply bringing this, then if you change the inequality, right? a less than equal to b is nothing but b minus a greater than 0, right? That is what. So in order to prove that, we can prove this, right? This one, right? So now we'll take x transpose x, y transpose y minus x dash y whole square. So that is, if we take y dash y transpose y out, then it becomes x transpose x minus x transpose y whole square by y transpose y. Just we need to practice this actually. Now y transpose y into x transpose x minus, so this we can just for mathematical convenience sake, we can split this into two parts, minus 2 of this term plus of the term, so that minus 2 plus 1 it becomes the same. This for mathematical convenience sake. Okay. Next, so this is what we got, right? So now we can divide this, we can separate this. This can be written as y transpose y x transpose x minus this can be written as x transpose y into x transpose y by y transpose y. Separating actually, if you see here, one more term x transpose y into x transpose y by y transpose y, and this term as it is. Just what we have done is this we separated into two terms. Okay. Now, so next what we have done is y transpose y. So from these two terms we have taken x transpose out, right? So then it becomes x minus y into x transpose by y transpose y. Next, from this we have taken x transpose y out, right? Okay. X transpose y if we take out, then we get x minus y. So if you see here, what we are trying to do is we are trying to factorize it. So now this is what we got, right? So same we are having this, right? So that means if it finally we'll get as y transpose y, and if you take this x minus y, this one, and this is x transpose, that means if you see here we are getting transpose of one other. That is actually, we need to practice to get how we have to do this simple manipulation. So that is, this becomes y transpose y, and this is what we got, right? If you see this one, so this is always greater than 0, and this y transpose, because this is one is, suppose z, if we take it's a transpose here, right? Z transpose is always greater than 0, y transpose y is always greater than 0, therefore the total it is greater than or equal to 0. That means x transpose x, y transpose y minus x transpose y whole square greater than or equal to 0, or we can write in the reverse. So this is the Cauchy-Schwarz inequality. So next some of the topics left in the discussion. What is definition of Riemann-Stieltjes integral, and state and prove first mean value theorem for Riemann-Stieltjes integral. And another important thing is the state and prove Cauchy residue theorem. And other one is Hadamard inequality is to be discussed, and also one problem which is simple on Jacobian to be discussed. Maybe we'll try to discuss these things in the later part. Thank you.